Okay, now we'll discuss about solubility equilibria. See, the concept solubility equilibria is applicable only for sparingly soluble salts. Okay, so this concept is applicable. Equilibrium exists only for sparingly soluble. So this concept is applicable only for sparingly soluble salts. Okay. Now, let me take one example. Say, I'll take silver iodide. I'll take silver iodide solid. Okay. If I put excess of silver iodide in a vessel containing water, okay, I'll take water as solvent. I have told you already. So, you take a vessel and take some amount of water and put this silver iodide. See, silver iodide is sparingly soluble. Therefore, most of the silver iodide solid settles down. It simply settles down, okay, as a solid. So this is silver iodide solid. And from this solid, few amount of silver iodide dissolves in water and form silver ions and iodide ions. We get silver ion and iodide ion, right? Because some amount of silver iodide dissolves in water and forms silver and iodide. Okay, as the time progresses, what happens is that this silver ion and iodide starts to combine and form silver iodide back. So, the solid silver iodide, right, initially dissociate to give silver ion and iodide ion in aqueous medium. Okay, so let me write here in water. In water, it dissociates to give silver ion and iodide ion. Initially, this process occurs in a fast manner. Then, after some time, what will happen? The silver ion and iodide ion, they recombine and form what is called the silver iodide. And this backward reaction will be initially slow and forward reaction is fast. Okay, as the time progresses, what will happen? At a particular time, the two process occur with the same speed. We call that stage as the equilibrium stage. Okay, so this dissociation attains equilibrium. Now we get silver ion in aqueous medium and we get iodide ion in aqueous medium. Right. Now listen carefully. Once we get the equilibrium, we can write the equilibrium constant. So what is the equilibrium constant? The equilibrium constant for this reaction is usually denoted as KSP, called solubility product constant. Solubility product constant or simply solubility product, which is equal to, this is actually equilibrium constant. How will you write equilibrium constant? It is the concentration of silver ion at equilibrium, right, into concentration of iodide ion at equilibrium, okay, and divided by the salt, silver iodide salt, concentration of silver iodide salt. And you know very well, for solid, concentration is always 1. Therefore, the solubility product constant is equal to concentration of silver ion into concentration of iodide ion. This product, the product of these two concentration will give you the solubility product constant for silver iodide. Okay, right? So this is what we call a solubility product. The concentration of these two ions. Okay, if you multiply the concentration of these two ions at equilibrium, we get the solubility product. And remember, solubility product, right? It also depends on temperature of this particular process. Okay, take note. I'll give another example. Now, let me give another example. Say, I'll take calcium oxalate, CaC2O4. Calcium oxalate, it actually settle down as solids in kidney. Okay, this is one reason. This is one of the solid that usually settles in the kidney as a kidney stone. right? Calcium oxalate. Listen, if I put calcium oxalate solid in water, suppose if you take some amount of water and add calcium oxalate solid. As discussed before, the maximum amount of calcium oxalate simply settle down. So this is calcium oxalate solid, and small amount of this solid dissociate and goes into solution. Okay, you will get what is called calcium ion and oxalate ion C2O4 2 minus. Okay, initially this process will occur, then after some time the two ions they recombine and starts to form what is called the calcium oxalate. Initially, the dissociation occurs faster manner, and the combination of the two ions to form the crystal or crystallization that occurs in a slow manner. After some time or at a particular time, the two process occurs with the same speed. We call that stage as equilibrium stage. Right? So at equilibrium, what will happen? See here. So this calcium oxalate solid. Okay. If you add this in water, what will happen? It dissociate and form calcium ion in aqueous solution plus oxalate ion C2O4 2 minus in aqueous medium or aqueous solution. Okay, and these two ions they also recombine and form the solid back. Okay, this forward and backward process will attain equilibrium at a particular time. Once it attain equilibrium, then we can write what is called the equilibrium constant. So what is the equilibrium constant? Equilibrium constant for this reaction, okay, is equal to, we write this equilibrium constant as KSP, also called solubility product constant, which is equal to concentration of the calcium ion in solution into concentration of the oxalate ion in solution divided by concentration of the salt. Calcium oxalate solid. And for solid, concentration is usually 1. So this becomes 1. Therefore, the solubility product constant for calcium oxalate is product of calcium ion concentration into oxalate ion concentration. Okay, this product will give you the solubility product constant for calcium oxalate solid. Okay, take. Right. Now we'll discuss the general the relation between solubility product and solubility for a sparingly soluble salt. Okay, so what is the relation? Relation between solubility and solubility product, okay, for a sparingly soluble salt. For a sparingly soluble salt. Okay, yes, how to do this? First, I'll take one example, then I'll give you the general example, a general relation. Number one. First, I'll take a general example, a specific example, silver chloride. Okay, and you know very well, silver chloride is an example for sparingly soluble solid. Right? If I put silver chloride in water, what will happen? Listen, suppose I'll take a vessel, I'll take some amount of water in it, I'll put excess of silver chloride. What will happen? Most of the silver chloride settle down and few silver chloride molecules, a few moles will dissociate and form what is called the silver ion and chloride ion. Okay, let us assume that then these silver ion and chloride ion, they recombine and form silver chloride ion. This forward reaction and backward reaction attains equilibrium after a certain time. Once it attains equilibrium, then the concentration of silver ion remains constant and concentration of chloride ion remains constant. Suppose, or we can say that the solution attains saturation. No more silver chloride dissolves in that. So I can say that the solution is a saturated solution. Suppose if the volume of the solution is 1 liter, okay, if the volume of this saturated solution is 1 liter, then the amount of silver chloride dissolved, okay, is nothing but solubility. Okay, so what I am trying to say is a silver chloride solid, right? It dissociate in water. It dissociate in water and form silver ion in aqueous medium plus chloride ion in aqueous medium. This we know. Suppose if the solution volume is 1 liter, okay, if the total volume of solution is 1 liter, suppose, right? In this case, listen, from the silver chloride, some amount is dissolved, right? Because of that, only we get silver ion and chloride ion, correct? What is the amount that is dissolved? It is nothing but the S, solubility. So, the amount of silver chloride that is dissolved, the small amount that is dissolved in water is what we call as solubility. Why? Because the solution volume is 1 liter now. Okay, so from this solid, I have excess of solid. From this solid, some S amount, S moles, S mole per liter is dissolved. So that if one molecule dissociate, I will get 1 silver ion, 1 chloride ion. Now S mole per liter is dissociated. So I will get S mole per liter of silver ion and S mole per liter of chloride ion. So this is the concentration of silver ion and this is the concentration of chloride ion. Right. Now, first we will write the equilibrium constant, then we will write the solubility. We will substitute the solubility. So what is the equilibrium constant? KSP. KSP is equal to concentration of the silver ion in the aqueous solution into concentration of the chloride ion in the aqueous solution at the equilibrium. And remember, the solution volume I have assumed as 1 liter. Right? If it is 1 liter, then if the solution volume is 1 liter, then this concentration is nothing but S and this concentration is nothing but S. Because in 1 liter saturated solution, the amount of silver chloride dissolved is nothing but solubility. Okay, if one molecule dissociate, I will get 1 silver ion, 1 chloride ion. If S mole per liter dissociated or dissolved in water, I will get S mole of silver ion, S mole of chloride ion in 1 liter of solution. Okay, therefore for silver chloride, KSP is equal to S square. Okay, KSP is equal to S square. Keep this in mind. Yeah, I hope you have understood the concept clearly. Now, let me move on to the next example. I'll take lead iodide. Okay. In a similar manner, I'll take a vessel containing some amount of water and I'll put excess of lead iodide. What will happen? The lead iodide solid simply settle down. This is lead iodide solid. Then from the lead iodide, some amount dissolved in water. Okay, so we get what is called Pb2 plus ion, and 2 iodide ion in solution. Then this Pb2 plus and iodide, they recombine and form what is called the lead iodide. Initially, the dissociation occur faster and the combination occur in a slow manner. But after some time, both will occur in the same speed called equilibrium. At the equilibrium, listen carefully, PbI2 solid, okay, in water, what will happen? It dissociate to give Pb2 plus ion in aqueous medium plus 2 iodide ion in aqueous medium. Each molecule will produce 1 Pb2 plus ion and 2 iodide ion. Then these ions recombine and form the silver iodide back. Okay, so the forward and backward reaction both occurs at the equilibrium, they occur with the same speed. Suppose if the volume of the solution, volume of this aqueous solution, and remember, once it attains equilibrium, then the concentration of Pb2 plus and iodide, everything remains constant. They need not be same, but remains constant. Okay, so I can say that the solution is a saturated solution. No more solid dissolves in that. It is a saturated solution. Suppose if the volume of the solution is 1 liter, then the amount of lead iodide dissolved in this water, okay, is nothing but solubility. Okay, so let us assume that from this maximum amount, say S mole S mole per liter is dissolved. According to the equation, if one molecule dissociate, I will get 1 Pb2 plus ion and 2 iodide ion. If S mole per liter dissolved, I will get S mole of Pb2 plus ion and 2S mole of iodide ion. Keep this in mind. Okay, now at equilibrium, we can write the equilibrium constant, also called Ksp. Ksp is equal to concentration of Pb2 plus ion in aqueous medium into concentration of iodide, and whatever stoichiometry number is there, put that number in the power. Okay, put the number in the power of the concentration, assuming that these are all simple reactions. So solubility product constant or solubility product is equal to product of concentration of Pb2 plus ion and concentration of iodide ion square. Okay, now if the solution volume is 1 liter, then the concentration of Pb2 plus ion is nothing but solubility S, and the concentration of iodide ion is nothing but 2S whole square is there. So what we get is an S into 2 square is 4 and S over 2, so we get Ksp equal to 4 into S cube. Right? This is the relation between solubility and solubility product for lead iodide sparingly soluble salt or for lead iodide salt. Okay, I hope you have understood this clearly. In the next example, I'll take a general expression, a general formula of salt, and we'll do that. Okay, yes. Let me take a general example. Right. Listen. Say instead of a specific salt, let me take a general salt. Say A, X, B, Y. I'll take some solid like this. Okay. It is assumed that it is a sparingly soluble solid. Now, if I add this solid in water, okay, if I add this solid in water, it will dissociate and produce X moles of A plus ions. Okay, so we get X moles of A, Y plus ion plus Y moles of B, X minus ion. Okay, and these two ions are formed in aqueous medium. Right, and these ions, they recombine and form the salt. Okay, this is in water. It occurs in water. Right. Suppose if the solution volume is 1 liter, solution volume, not the solvent volume, solution volume. If the solution volume is 1 liter, and at equilibrium, the concentration becomes saturated or become constant. See, at equilibrium, the solution is actually called a saturated solution. Right. If the solution volume is 1 liter, then the amount of the solid dissolved in water is nothing but solubility. So which is nothing but S mole. So from the amount, whatever amount we don't know, from the amount S mole is dissociating. Therefore, S mole per liter is dissolved. So we get X into S mole of A cation and Y into S mole of the B anion. Okay, now first I'll write the solubility product for this salt. Solubility product equal to concentration of A, Y plus ion power X at equilibrium into concentration of B, X minus ion power Y at equilibrium. If the solution volume is 1 liter, then this concentration is nothing but X into S power X, and this concentration is nothing but Y into S power Y. Okay, or I can write Ksp equal to X to the power X into S to the power X into Y to the power Y into S to the power Y. Or I can write Ksp equal to X power X, Y power Y into S to the power X plus Y. This is the general relation between solubility product and solubility of a sparingly soluble salt. Okay, how to use this relation? Yes, we'll discuss this in the next lecture. Okay, thank you.